What's up, everybody? Phil here. Thank you for joining me for part 4 in our series on coding a neural network from scratch. When we left off last time, we had just finished calculating the activation function and visualizing it. I did leave out one thing, so we are going to have to calculate the gradient of our activation function, and that's pretty simple. If you're familiar with calculus, then it shouldn't be any surprise to you, but the gradient is just going to be proportional to the function itself, and that's a hallmark of the exponential functions. So our gradient of the function is just going to be s times 1 minus s. And we won't bother visualizing this, but we'll need that later. So I really want to move on with some of the actual details of a neural network, because it kind of feels like we've been playing around with all of this stuff that is only tangentially related. I mean, of course, we have to build the groundwork, but it's time to actually get into a little bit more of neural network type stuff. So one of the things we're going to need to implement is what's called a cost function. So your output of your model isn't always going to be correct. Sometimes it's going to mistake a dog for a cat. And in particular, it'll do this early on when the model is just starting out. And the reason is because we're going to randomly initialize our parameters of our model. And so it's going to start out in some random part of parameter space. And so, as you might expect, the output of the model in the beginning isn't going to be pretty correct. So you want the model to be able to learn from its mistakes. And the cost function is just a mathematical penalty for being wrong. So it's going to have some value in proportion to the wrongness of its prediction. So if it gets a prediction right, it's not going to incur any penalty. If it gets it completely wrong, it'll incur some large penalty. And the consequence of this mathematically is that we're going to end up with this complicated function, this cost function, that varies based on parameters. And this is just a two-dimensional projection, right? These parameters are going to be multi-dimensional, so you can't really visualize it. So we just take kind of a cross-section in normal space to visualize it. But you can see that the cost function is going to have some really complicated dependence on those parameters. And there are many local minima to get trapped in, right? So what's going to happen is you're going to take in a training example, it's going to feed it through the network using its randomly initialized weights, it's going to get some cost, and it's going to say, okay, I am at some point in parameter space giving me some certain cost. What do I do next? It's going to make a jump in parameter space to some other combination of parameters and try that out. The way it does it is by taking the gradient of the cost function with respect to those parameters, the derivative. So you can see that at minima, it's going to have a very small gradient, right? If it's at a true global minimum, it's going to have no gradient at all, and that's where we want it to converge to, the global minimum, which is to say the true set of parameters that exactly fit that particular training example. And one thing that can happen is that each time you make a step, you can sometimes bounce back and forth, right? It's not hard to imagine that if you take the gradient and move too large in this direction, that you can end up just oscillating back and forth between these two parts of the function. And so we're going to need something called a learning rate that dictates the size of the steps that it takes in parameter space, right? It could change the parameter by 0.01, by 0.1, by 1. It could change it by any number, so we have to dictate kind of a baseline number for it to move around. And then we can dictate another parameter that tells it as it evolves through time, how does it act with respect to those jumps? Does it take smaller and smaller jumps as the model gets better and better? So that way you converge to a global minimum. You do what's called annealing. And that's indeed what you want, right? As the model learns, it's going to get better and better. It's going to get closer and closer to this point, the true global minimum, hopefully. But it'll never get quite there. So you want to be able to minimize the probability it's going to overshoot this, right? You don't want it to go from this point here to that point over there. And so we're going to have to encode in all this information into a mathematical function. And I have a prettier picture here that is a three-dimensional representation of kind of a cost function. You can see it's like a heat map where red is a high cost, blue is a low cost. And I stole this from somebody on the web. I'm putting it here unattributed, but I think they got this from the Coursera class. So that's the basic idea of a cost function. You want to associate some penalty with the wrongness of the model, and you're going to want to navigate that space with respect to your model parameters. Now, one other thing we have to deal with is something called bias units. So just consider the case of simple linear regression. You're trying to fit a straight line, right? You could say y equals mx, and then you get a line that passes through the origin. But maybe there are solutions that you want that don't pass through the origin. Well, how do you get those solutions? You add in an extra parameter, the y equals mx plus b, that allows you to shift this line up and down to better fit your data. That b is just an example of a bias unit. Okay, so you're just adding one extra parameter to your model. And so we're going to do the same thing in neural networks, where we're going to actually add bias units to each layer of our model, with the exception of the output. So we're going to add an extra bit, an extra unit to the input data, as well as an extra unit to the hidden layers. And this bias unit, by convention, just has a value of +1. And we don't do any real calculation with it. It's just kind of there to feed forward into the next layer. It doesn't take any input on its own because it's a constant, but it just feeds forward into the model in subsequent layers. So to recap, we have a complex function called the cost function that associates a penalty with the wrongness of the model, and it has a very complicated dependence on the parameters. The algorithm is going to take steps in parameter space in an attempt to go from some local minimum or maximum all the way down to the global minimum. It's going to accomplish that through taking steps in parameter space based on the gradient of this cost function with respect to its present position, and it will take steps dictated by some parameter called a learning rate, and then we're going to have another parameter associated with the overall learning of the model as a function of time to help it anneal to this global minimum. And we're also going to add in what are called bias units that don't change as a function of any inputs, but are just there to help us better fit the data. Now, if any of this is confusing to you, I highly recommend you take the Coursera course on machine learning by Andrew Ng? Not sure how to pronounce his name, but it's the Stanford course from, I think, 2011. The material is a little bit dated, but it gives you a phenomenal foundation in the algorithms of machine learning, and it's taught using MATLAB/Octave, so it's very easy to do, very kind of conceptual heavy. You don't need to know any programming in Python or anything like that. It's a tremendous course, and we're going to rely a little bit on the material from that course. So I encourage you to take it. It's completely free. You can pay if you want to get a certification, but you don't have to. That's completely and totally optional. So let's talk about the cost function, and for that we're going to go ahead and take a look at the notes from that Coursera class on machine learning. I'm going to go ahead and blatantly rip this off. Again, I recommend you take it. But for a neural network, this cost function is going to be pretty complicated. This is the mathematical representation. We're going to use what's called a vector representation, so it's going to be pretty easy to implement. But the key thing to note here is that it's proportional to these y sub k's superscript i's. These are just the training. Training labels from your model, right? And this h of theta as a function of x is just the model output. So it's proportional to the log of the model output plus 1 minus the label times the log of 1 minus the output. And then you have this other term here that we won't implement in this part of the tutorial series. I'll probably get to it later, but this is a penalty with overfitting. This is called regularization, and you have this parameter lambda that associates a penalty with overfitting your data. So one of the dangers of all of these machine learning algorithms is the danger of overfitting your data. So what that means is you get a solution that is really, really awesome for your training data, but doesn't generalize at all, right? That is completely useless because the whole purpose of all these algorithms is to make real-world generalizations. So regularization is a way of associating a penalty with overfitting in your model. We won't bother with it just yet. We'll get to it later. You'll see that we don't have that danger for this training set. This is a fairly simple and straightforward problem. So I want to start with calculating that cost function. So let me go ahead and bring that back up. So just to show you how it works so you can see them side by side, we're going to want a function called calculate cost, and we're going to want our y encoding and our model output. So this y sub enc is just this y sub k here, and output is just the h of theta of x of I. So that's the output for the ith training example. And so the first term, which is this here, is just going to be equal to minus y enclosed times np.log of output. Okay, so you have, don't forget the minus sign here, you have y sub k, the y enc of log of h of theta, log of output. And these are all represented by NumPy arrays, so this does an automatic vectorized representation. So we don't have to account for this sum because we're using the vector representation. If you go through the course, you'll see that these sums are just there to account for the fact that you're multiplying matrices and vectors together. And our second term is just going to be 1 minus y the output, the training label times np.log of 1 minus output. And so then the cost is going to be the sum of those two NumPy arrays. And I put in the difference, sorry, to account for that minus sign because you got the minus sign out front. So it's just minus this plus that, right? And then we just want to return that cost function. And it's really that simple. So again, all we've done is a vectorized representation of this mathematical equation. And this is the cost function associated with a single training example at some point in parameter space. And so our next step is going to be to go ahead and add in the bias units. It's another kind of bookkeeping type thing, but it's pretty straightforward. So we have to account for two different cases. So we have a matrix representation of our model, and so we can add bias units either on rows or columns, and we want to do both depending on what operation we're trying to perform. You'll see that we're going to have to perform, we're going to have to operate on transposes of these matrices, so we have to account for both ways because we do a little bit of playing around with multiplying matrices and their transposes, and so we have to be able to add in bias units in both different ways. So say def add bias unit some matrix X, and we're going to call it where, meaning where is just row or column. Where do you want to add the bias unit, to a row or a column? So if where is column, then we want to create a new array that's just filled in with ones, and we want to add it along the column, right? So the second of our dimensions. So what we've done here is we've created a new array that is the same size as our old one with an extra column, and we're going to assign our rows and from column 1 on to our previous array. So we have some array, it's a matrix X, and we want to add one column of just ones to the beginning of it. And so this command here creates a new array with an extra column, and it's all the columns are just ones. And so then you're saying that the from first column on, because Python indexes from position 0. So column 0 is just going to be all ones, and column 1 on is going to be our new array, our old array, sorry. So that essentially creates a new array with the first column being all ones. So we can do something similar for the rows. Xnew is empty.ones, shape, in this case 0 plus 1, because we're going to add a new row, shape 1, and Xnew from the first row on, all columns equal X. That, for some reason this Atom editor does funny stuff with X. So that's all there is to it. We just return Xnew. So now we have the cost function and our bias units, and we're getting close to starting learning our neural network. So the next bookkeeping thing we have to take care of is initializing our weights to some point in parameter space. And so if you look at our neural network we're going to be building, you have two sets of hidden layers. And these arrows are the elements of these weight matrices. And so you can see we're connecting every node of the input layer to every node of the hidden layer. And there's going to be a bias unit here, here, and here that'll have weights leading to it as well. And so we have weights connecting the input layer to the first hidden layer, weights connecting the first hidden layer to the second hidden layer, and weights connecting the second hidden layer to the output. Now the dimensionalities of these are going to be different, right? We know that we have, in our input layer, we're going to have a 28 by 28 matrix that corresponds to the bytes of our image that we flatten into a column vector and add a bias unit. So the input layer is going to have dimensionality of 785 rows, one column. Our input layer, our hidden layer is going to have some combination of units, and that's a parameter you can play with. We'll get to that in a later video. We're just going to start with some value. We're going to pick a value out of thin air and go with it. And in general, you want your two hidden layers to have the same numbers of parameters, but those can be different from your input layer. And then your output layer is just going to have as many units as you have outputs. So in our case, it's going to be a 10-unit output layer. So we want to initialize these weights that connect our input and hidden layers to the output with just random values. We want to start out at a random point in parameter space. Now you don't want to start out at 0, because if you do, your model isn't going to do anything, right? You're just going to get trapped in some funky part of parameter space of all zeros, right? If you're multiplying 0 by some number, you get 0, so you don't do anything in the model. It's totally useless. So we have to initialize our weights with some random numbers from parameter space. So we want to know the number of features, the number of hidden units, and the number of output units. So again, number of features is just the inputs. So we have a 28 by 28 matrix that we flatten into an array or a column vector. So we're going to have 784 features, and we're going to have some number of hidden, and we're going to have 10 output units. And I guess I could just say n output equals 10. I didn't bother, but if you want to be pedantic to be consistent with the number of labels in the encoding one-hot function, that's fine as well. So W1, we're going to want uniform random numbers, and we're going to want to go from minus 1.0 to 1.0, and the size is going to be the number of hidden units times number of features plus 1. And so now that I'm looking at this, I think we may actually have to add a plus 1 to the number of hidden units, because we're going to have bias units. I'll have to think about that and come back to it later. And then we're going to want to reshape this because this comes out in the kind of wrong dimensionality. And we can do the same thing for the second weight, W2, random.uniform, minus 1.0 to 1.0, size, n hidden times n hidden plus 1. What am I doing? We don't need that extra parenthesis. Okay. And then we want to reshape that again. And then our output is our final set of weights is going to be for connecting our second hidden layer to our output layer. And again, another random uniform set of numbers. Size equals n output times n hidden plus 1. And we're going to want to reshape it. And then we're going to want to return our 3 weight matrices. So what have we done so far? We have covered the need for a cost function to associate a penalty with the wrongness of our model. We incorporated a way to add bias units to make sure we get meaningful solutions, and we have initialized our model to some random point in parameter space. So next up on the docket is to perform the model feed forward, and which means taking our inputs and feeding them all the way forward, multiplying them by weights to get the actual output of the model. And the final step will be to implement a gradient function with respect to our parameter weights, and then encode the actual run model function to enable learning. And then we'll be able to actually see how well our model performs. And it won't be spectacular, but this is a really naive implementation, very basic. And you'll see it actually has pretty decent accuracy. And that's quite startling that something so simple would have such reasonable accuracy. So I'm going to go ahead and pause it here. And I thank you all for watching. If this has been helpful for you, please hit the like button, subscribe for more content, and I'll see you guys in the next video.